Assalamu alaikum students. So today what we are going to do, we are going to derive an equation of head loss by using our energy equation, and then we will see how we can derive some equations for turbulent flow. Just to remind you that turbulent flow is very difficult to derive theoretically, so we will be relying heavily on the experimental equations that were derived empirically by doing a number of experiments to derive different equations of their velocity flow profiles and equations like these. So let's move on and do that. So now to take into account the head losses, we will take the energy consideration. As you remember, when we talked about losses, when we were deriving the Laminar transport theorem for the second law of thermodynamics by taking energy as our extensive property, we came up with the losses. There were two types of losses. One was the head loss and one was the loss in the shaft. So for energy consideration, we will be using our Reynolds transport theorem, the energy equation that we derived. This is the energy equation. This is the energy equation that we derived using the Reynolds transport theorem by taking energy, the specific energy as our, here it is intensive property, but the total energy comes out to be the sum of the net heat transfer in and out and the net power transfer to the shaft in case of pump and turbine. So now we will simplify this equation by making an assumption that our flow is steady. Our flow is steady. So by making this assumption, any integral involving change with respect to time will be converted to 0, and we will be left with the control surface integral, and on the right hand side the net heat transfer and the net work transfer or the net power transfer. So let's apply this equation after simplifying it to this scenario, the stream tube, and this stream tube has one inlet and one outlet. So we will apply this control surface integral to these two control surfaces on the inlet and on the outlet. We already did that, so you must be familiar with this, and this is what we get when we apply this control surface integral to this inlet and outlet. So this is our equation now. This comes out to be the mass flow rate. This is the change in energy. This is the change in pressure at the outlet and inlet. This is the change in kinetic energy and the change in potential energy, and the right hand side will remain as such. So now let's move a step further and divide the right and left hand side with the mass flow rate and write this equation in the form of this equation. You already know what this is. This is the Bernoulli equation that was derived along the streamline. So we can arrange this equation above in this form. So we can write this equation in this form, and this is how we are going to do that. We will take the pressure energy, the kinetic energy, and the potential energy at the outlet, write it on the left hand side, and these three terms for the inlet on the right hand side minus these terms plus the net work done by the shaft. So now these three terms are in a single bracket because if we divide the right hand side and the left hand side by g, by the gravitational acceleration, we will get this term in terms of head losses, and this is what we are interested in because we want to find the head loss inside the pipe. So divide both sides by gravitational acceleration g, and we will get this term. We will get each term in terms of heads. You are already familiar with this equation. This is the pressure head, velocity head, elevation head at the outlet, and the pressure head, velocity head, and elevation head at the inlet. Similarly, this will come out to be the head loss, and this is the loss due to the shaft. It can be positive or it can be negative depending if it is a pump or if it is a turbine. So here we are just dealing with the pipes. We are not actually considering any pump or turbine. So we will remove this term, and now let's move on and do that. So this is what we came with, and this is how we will write this equation. Further, we will remove this term because we are not dealing with any pump or turbine. We are just simply taking a pipe flow, and now you can see that our output and input are replaced with 1 and 2's. And now you can see the alpha term. The alpha term is the kinetic energy correction factor. This is the kinetic energy correction factor. And why are we putting alpha with the kinetic energy correction factor? Because the velocity profile inside the pipe is changing. The velocity profile, if we are taking laminar flow, so the velocity profile turns from the uniform to transition to parabolic phase. So to compensate this profile change, to compensate this velocity profile change, we multiply a correction factor with the kinetic energies at the inlet and at the outlet. So that's why we take alpha. Alpha is just a kinetic energy factor to compensate the velocity profile change when the flow fully develops. So this alpha has a value of 1 for uniform flow. It has a value of 1.05 to 1.10 for transitional flow, and it has a value of 2 for a fully developed parabolic flow. So depending on the flow that you are dealing with, you can actually put a value of alpha and multiply it with the kinetic energy terms. But since this is what we did, this is what we assumed by, as you can see in this equation, and this equation we write the average subscript with the kinetic energy terms, because what we assume that our velocity profile is the average of whatever velocity profile that is being developed. So this is already uniform velocity profile, and to make this velocity profile uniform, we take the average of this velocity profile. So we come up with this average velocity profile, the one that is with red color. This is the average velocity profile, and similarly for parabolic velocity profile, we also assume a average velocity profile. So that's why normally we don't take the alpha term in the equation, but whenever we are considering the velocity profiles and we are taking account the change in the velocity profile, then we multiply the alpha term, that is the kinetic energy correction factor, and these are the values for different velocity flow profiles. And as you see, the velocity profile, the correction factor for a uniform flow is 1. So if you have, I put 1 here, so it does not will have any significant effect on this kinetic energy. So this is why we take the average. We write average with the kinetic energy terms in this equation. So for fully developed flow, the velocity profile does not change, as we already discussed that when a flow is fully developed, then its profile, if it is a laminar flow, it will remain parabolic. So for a fully developed flow, the velocity profile does not change. So if we say that at point 1 and point 2 the velocity profile is fully developed, so these two kinetic energies will be equal at point 1 and point 2. There will be no change because the flow is already fully developed. This is our assumption. So by making this assumption and putting it in this equation, this is what we will come up with. So this is our equation for the head loss, but we will take it a step further and we will simplify it a little bit further by taking that the point 1 and point 2 of the point 1 and point 2 in a pipe are at the same elevation. So Z1 is equal to Z2. So these two terms will also cancel out. And what we will be left with, we will write it as such that delta P over gamma is equal to our head loss, and we already have our equation for pressure drop. So let's write that equation, and that equation is, if I write it here, that delta P is equal to 4L dot W over D. So let's put the value of delta P in this equation, and we will come up with an equation for our head loss, and that will be 4L dot W over gamma D. You can further simplify it by taking D, and as you know that R is equal to D by 2. R is equal to D by 2, so you can put D is equal to 2R, and you can actually switch this D with 2R. So let's do that to get our final equation for our head loss. And now our final equation for head loss will be HL is equal to 4L dot W or gamma or 2R. So this is our final form of head loss equation, and this is what we are going to use whenever we are going to find head loss in pipes and when the flow is laminar, because remember we are still dealing with laminar flow. So now in the next slide we will discuss turbulent flow and how we are going to develop some useful equation for that flow. So let's do that. Now before moving on to a turbulent flow, let's look at what we described the laminar flow as. And for laminar flow, we said that the laminar flow was steady. And what did steady flow means? That if we take velocity, so velocity will be only a function of the spatial coordinates like the x, y, z coordinates. We will not be looking at velocity as a function of time, but only as the function of the spatial coordinates x, y, z axis. And viscous forces are maximum for laminar flow. For laminar flow, viscous forces are maximum as compared to turbulent flow, because as you remember the velocity profile of laminar flow, it was parabolic, and it was parabolic due to the no slip boundary condition near the walls of the pipe. And as you remember for turbulent flow, the turbulent flow velocity profile was more flatter. It was more flatter as compared to the laminar flow. That's why that's what we assumed, because the turbulent flow profile was constantly changing. That's why we took the average of all those velocity profiles and came up with the flatter velocity profile. And we also saw that the viscous forces near the wall in case of turbulent flow are minimum as compared to laminar flow. So viscous forces are dominant when we are talking about laminar flow and not much dominant when we are talking about turbulent flow. So turbulent flow, for turbulent flow, what we are going to say that if we take turbulent flow, it is first unsteady. It is unsteady flow because if we take velocity, so velocity will be the function of both the spatial coordinates and time. Means velocity will change with both the position and time, and it is three-dimensional in nature, and viscous forces are minimum as compared to laminar flow. So if we look at this diagram, you can see that velocity is plotted with respect to time, and you can see the line that it is very unsteady. So this is an unsteady velocity profile, and what we will do, we will take 2 points on this profile. One will be the mean velocity, that is the mean velocity, and this one is the peak velocity, and we will write it as such that the total velocity will be equal to the mean velocity plus the peak velocity. Peak velocity is the u dash. So this is the total velocity, and to write equation for shear stresses in turbulent flow, this is what Reynolds came up with, and this equation was derived by empirical analysis. Means that he came up with this equation by doing a number of experiments. So this is what we did in in laminar flow. We actually developed mathematical modeling for different flow rates, velocity profiles, and head losses. But in turbulent flow, we rely much more on the empirical data, on the experimental data, because we cannot develop a considerable amount of theory for turbulent flow, because it is very hard to do so, because as you can see, this line is very unsteady. So how can you write equation for such a line? So that's why a lot of equations are derived from experiments for turbulent flow analysis, and this is one such example of a shear stress that is being derived by Reynolds, and this is Reynolds expression for turbulence. This is called the Reynolds expression for turbulence. Now, for turbulence, we also have a work of a scientist. His name was Prandtl. He was a German scientist, a physician, and a physicist. Sorry, and he came up with his own equation of turbulent shear stress. And let's look at that. So before discussing the Prandtl equation, what we are going to do, what actually he did, he divided the velocity profile. This is the turbulent velocity profile you are already familiar with. He divided this turbulent velocity profile into three layers. One is the viscous sublayer that is near the pipe. This is the pipe, and this viscous sublayer is near the pipe. So he actually assumed that in this layer the flow will be laminar. Then there is an overlapping layer, or you can say a transition layer, and then in the outer layer the flow is fully turbulent. So he actually he also came up with these layers by looking at a number of experiments. So this is what our new equation for shear stress will now be, and this will be the addition of laminar shear stress plus the turbulent shear stress, the one that Reynolds derived. So you are already familiar with this equation, that shear stress is mu and the velocity gradient, and this is what we already derived for Newtonian fluids, but that is for laminar flows. But as you can see, we have a laminar sublayer near the pipe right here, the viscous sublayer. So that's why he added these two equations right up here. So this is what Prandtl came up with, and he went a step further and also considered that small roughness on the pipe surface disturbs the viscous sublayers. So to replace this term, he came up with the term of eddy viscosities, and now you can see that here the turbulent velocity, the turbulent shear stress is equal to eddy viscosity. This is the eddy viscosity multiplied by the mean velocity gradient. So he came up with his own term of turbulent shear stress, and this is the Prandtl equation for turbulent shear stress. And he went on with the help of experiment. Also he came up with the term for eddy viscosity, and this is the term for eddy viscosity, and that term is equal to the rho, that is the density. He also came up with the term of mixing length. This is the mixing length, and the mean velocity gradient. So what is the mixing length? This is Prandtl's theory, and to look at Prandtl's theory, we will look at what mixing length is. So what he said, that in a turbulent process, what the fluid particles does, the fluid particle travels in bulk, and from moving from one layer to another, means that this is one layer of fluid and this is another layer of fluid. So the fluid particles actually travel from one layer to another in bulk, and the distance they cover from one point to another, that distance is called the mixing length. Because as you can see that in laminar flow, the flow the streamlines are actually parallel to each other. That is a laminar flow. But in turbulent flow, the streamlines are not parallel to each other, but they are already mixing. So he came up with this term of mixing length, and if you read the statement, that the turbulent process could be viewed as a random transport of bundles of fluid particles over a certain distance, and that certain distance, the mixing length, from a region of one velocity to a region of different velocity. This is why turbulence occurs, because there are different regions of velocity, and we don't have different regions of velocity in laminar flow, but only in turbulent flow. So due to that velocity gradient, that is why the mixing occur. So he also came up with another term, and what he did, he assumed a pipe surface, and he said that the mixing length is a linear function of a distance y from the pipe. That as we move away from the pipe surface, this is the pipe surface, and as we move away from the pipe surface, then the mixing length will increase. Means that if a flow is turbulent, then the particles will travel over a maximum length from one velocity region to another low velocity region, or and as such. So he came up with an equation for that, the mixing length Lm is equal to ky. This is called Karman's constant. This is called Karman's constant, and all these equations that I am writing, they are not actually derived, but he came up with. He came up with these equations with the help of experiments, and the value of Karman constant is 0.4. This is also what was assumed from the experiments. So now what we will do, we will actually put the value of the mixing length in this equation, and we will derive it further to get our equation for velocity profile, and that velocity profile, as you already know, is turbulent. So we will like to write equation for this turbulent velocity profile. So now this was our shear stress, our shear turbulent stress, and that shear stress is equal to the density, the square of the mixing length, and the square of the mean velocity gradient. And now what we will do, we will actually write the value of mixing length, that is Lm is equal to ky, and we will put it here. So our equation will become, we will put a bar over here, and that is density ky whole square du bar over dy whole square. So simplifying it a bit further, we will take this term to the left hand side, and these terms will divide it over here. So now we have du over dy whole square is equal to r dash over rho ky whole square. I would suggest that you write these equations along, because you will not find this derivation in your Munson book. So now taking the under root on the both sides, this is what we are going to come up with. If we take under root on the both sides, so we will come up with du dy is equal to 1 over ky under root dot dash over rho. So now here we came up with an interesting term, and if you look at this term, and you write the dimensions of shear stress and density, so we will come up with the dimensional formula of L over T, that is length over time, and that length over time is equal to meter per second. So what does meter per second is? Meter per second is as you already know, is velocity. So this is what this term will be. We will represent this with u star, and that u star is equal to dot dash over density, because we already know that that's its units is meter per second, so we can represent that as u star, and that u star is called the shear velocity. This is the shear velocity. This is called the shear velocity. So now we will take the value of shear velocity and put it in this equation. So we will free some space for ourselves first. And write the equation now. So our equation will now look like this, that d u dash over dy is equal to 1 over ky u star, the shear velocity, and by taking dy to this side now we can integrate it. So let's do that. Du is equal to u star will come out of the integral over k, and the integral will contain dy over y. So now after integrating this, what we will get integration on both sides. So after integrating this, what we will get u is equal to 1 over k u star natural log of y, because this is what we will get if we integrate this, plus constant of integration, because we are integrating this equation without taking limits for our integral. And as I said earlier, when we integrate without limits, we are ended up with a constant. So to see what the value of this constant will be, we will take a boundary condition, and for our boundary condition we will say that let's say we have a pipe, and let's say we have a pipe like this, and this is the axis of this pipe, and this pipe has a certain radius of r, and the radius here right at the center is maximum, so we will take that as y is equal to r, and the radius at the wall is 0, so we will take that as y is equal to 0. So if we take our radius at this point at y is equal to r and put it right here, so we will get our value of c. So by putting y is equal to r from this boundary condition, we will get our value for our constant c. So let's write that will be, and at the center of this point, at this center point, our velocity will be maximum, because this is the mean point of this pipe. So at the mean, the velocity is already maximum, so we will write it like this, that u maximum is equal to u star over k natural log of r plus c, and c will be equal to u maximum minus u star over k multiplied by natural log of r. So this is our value of c. Now we will put the value of c in this equation. We will put the value of c in this equation right here. So let's free up some space first. So now let's write our equation. After taking the value of c in this equation, we will get u is equal to u maximum plus u star over k, and we will get that sorry, excuse me, I'm writing the wrong equation here. This will be the equation. U is equal to u star over k natural log of y plus u maximum minus u star divided by k and natural log of r. So now let's refine this equation a bit further. U is equal to u maximum, and we will subtract these two terms by taking u star over k common. So plus u star over k into natural log of y minus natural log of r. So we can actually simplify it a bit further by taking the natural log as y over r. So u is equal to u maximum plus u star over k natural log of y over r. So k is a constant, and its value is 0.4, and putting the value of k as 0.4, what we will get the final form of our velocity equation, and that will be also called the Prandtl velocity distribution for turbulent flow. So u is equal to u maximum plus 2.5 u star natural log of y over r. So this is our equation for velocity distribution, and this is also called Prandtl's velocity distribution, and this will be applicable both to smooth pipes and to the rough pipes. So now let's see how we can actually further simplify this equation, and how we can actually draw some lines with the help of these equations after simplifying it. Now in the previous slide we derived the velocity distribution, the Prandtl's velocity distribution formula, and let's write that again. That is u is equal to u maximum plus 2.5 u star natural log of y over r. So let's simplify that a bit more, and u minus u maximum will give us, or if you can write it like this, that u maximum minus u will give us minus 2.5 u star natural log of y over r. And to take this minus sign, this negative sign out, we can actually flip these two ratios, and this minus sign will be cancelled out. So let's do that. So we will end up with u maximum minus u is equal to 2.5 u star natural log of r over y. So now this is what we came up with, and this is what this equation actually looks like. This is the u maximum, which is the velocity at the center line. This is the u dash, the mean velocity, and we will divide the u star over here, and that is our shear velocity, and the rest is on the right hand side, that is 2.5 natural log of radius of the pipe divided by the radial distance covered. So this is our velocity distribution formula, and to write it in power law velocity profile form, the power law velocity formula came up from experiments, and we can write it like this. This is the power law velocity profile, and this velocity profile formula, the power law velocity profile formula, is used to draw the lines of turbulent velocity profile. As you remember, when at the start of laminar flow, when we analyzed the laminar flow, what we did, we actually derived an equation for shear stress, and then from the shear stress equation we derived the equation for our velocity flow profile, and we came up with the parabolic velocity flow profile. But to do that for a turbulent flow, you already know that is already very difficult because of the unsteady nature of the flow. So what we did, we relied heavily on the empirical terms, the terms that we got from experiments, and this is also another power law velocity profile formula that we empirically got. Empirically means from experimental results, and we use this velocity profile formula to plot the lines for our turbulent velocity flow. And as you can see, this n right here, this n right here is a function of Reynolds number from this graph, from this figure 8.17 from your Munson book. This is the exponent n for power the velocity profile, and as we increase n, our Reynolds number also increases. So n is a function of Reynolds number, and if we use this equation to plot the lines, so we come up with these lines, and these are different lines. This is n is equal to 6, n is equal to 8, n is equal to 10 by putting in different values of n. So this is as you can see, the laminar line here, the laminar flow line here is much more parabolic. It is parabolic in nature, but as we increase the value of n, it becomes turbulent. The lines become flatter and flatter. So that's why we drew the velocity profile of turbulent flow flat. We actually already discussed that the velocity profile of a turbulent flow is much more flat as compared to a parabolic, which has a much more curvature. So this is our empirical formula, and it is still not sufficient, because if we put the value of n 0, it means that near the walls is, if we like to see the velocity turbulent profile near the walls, so what will happen? This will goes into infinity. So this is not sufficient for us, but we can make do with it, and we can actually plot some lines for higher values of n, but not n is equal to 0. So this is what this diagram shows, that n is actually the function of Reynolds number, and as we increase the value of n, it goes into the higher Reynolds number region. And by using this equation and plotting the lines by using this equation, we can actually see that the velocity profile lines, these are the velocity profile lines for turbulent flow, they become flatter and flatter. So our assumption that we take the average of all the turbulent velocity profiles and make a flat velocity profiles, that assumption actually came up from here. That's why I put this diagram here, so that we have more clarity about our turbulent velocity profiles. And again, I would like to repeat that turbulent flows are very unsteady, and that's why deriving a theory for that and deriving equation from that theory are near to impossible. So we will have to heavily rely on empirical data to actually come up with velocity profiles like this. So now let's have a look at this example in which we have to see the laminar pipe flow properties, and given is flow rate of a corn syrup through a horizontal pipe. As you can see in this figure, there is a corn syrup flowing through this pipe with a certain flow rate, and the length of the pipe is 6 feet, and there is a pressure gauges at 0.1 and 0.2. So there is a pressure difference at 0.1 and 0.2. So it is proposed that Q is equal to K delta P, that is that the flow rate is equal to the calibration constant, that is some constant, into the pressure drop. Your calibration constant K is a function of temperature T, because the variation of syrup's viscosity and density with temperature. So K is a calibration constant, and it is a function of the temperature, and these variations are given in this table right here. As you can see, that these variation with respect to temperature is of density and viscosity is given in this table. So what we will have to do in part A, there are 3 parts. In part A, we will have to plot the calibration constant values, that is the function of temperature versus temperature for a temperature range of 60 Fahrenheit to 160 Fahrenheit. So we will plot a calibration constant and temperature graph, and part B is determine the wall shear stresses. Determine the wall shear stresses and the pressure drop delta P for Q is equal to, for a flow rate of this 0.5 cubic feet per second and temperature of 100 Fahrenheit. So part C is for conditions of part B, determine the net pressure forces. So we will find the pressure forces, that is area into delta P, and the net shear forces, that is area into the wall shear stress on the fluid within the pipe between section 1 and 2. So let's see how we can plot the graph between the calibration constant and temperature first. And for that, this is our solution. We will first use the flow rate equation for our laminar flows, and this is our flow rate equation in which we have pi d power 4 delta P over 128 mu and L. So what we will do, we will put the values that we have. We will put the values of pi, we will put the values of our diameter, that is diameter is 3 inches. Here it is 3 by 12 because we will have to convert that into feet. And then we don't have any value of delta P, it will remain as such. Then in 128 mu and 6 feet. So what we have, we will solve it, and we will get an equation like this, that Q will be equal to 1.60 into 10 to the power minus 5 divided by viscosity into delta P. So in this equation we had two unknowns, that is delta P over mu. So delta P over mu will remain as such, and we will compare this equation with the equation that we were given in the statement, that Q is equal to K delta P. So if we compare these two equations, we can see that the value of K can be extracted from this equation, that K is equal to, as you can see, 1.60 into 10 to the power minus 5 over mu. So we will use this equation to plot the graph between the calibration constant and temperature, and for that we will use our table. We will take the values of viscosity at different temperatures. We have a temperature range from 60 Fahrenheit to 160 Fahrenheit, and we will use that temperature range. We will use this temperature range, and for 60 Fahrenheit we will take the viscosity value this, and we will put it in this equation. And similarly for 80 Fahrenheit we will take the value of viscosity as such, and so on and so forth until 160 Fahrenheit, and we will get different values of K, and we'll plot that with respect to different values of the temperature that are given. So this is how our graph will look like. So as you can see that the calibration constant is dependent on the temperature. This was our first part, and in the second part we have to find the wall shear stress and the pressure drop delta P for the flow rate, that is 0.5 cubic feet per second, and temperature, that is 100 Fahrenheit. So we will again use this table to plug in our values of densities and viscosities wherever they are needed, and we will use this 100 Fahrenheit temperature to plug in these values. So let's move on. So these are our values at T is equal to 100 Fahrenheit for viscosity, as you can see from the table, and for flow rate that is given 0.5 cubic feet per second, and the pressure drop according to equation that we have for laminar flow is this. So delta P is equal to 128 mu L Q divided by pi d power 4. So all the values are given. We will just put in the values and make sure that every length dimension is in feet, and we will get the value of our pressure drop. Then to actually see that the flow is laminar, we will find the Reynolds number, and to find the Reynolds number, because we are using the laminar flow equations of pressure drop, so just to make sure that our calculations are correct, we will first see that whether our flow is laminar or turbulent. So for that purposes, what we need to do, we first need to find the velocity, and then we will find the Reynolds number. So V is equal to Q over A. As you can see, this is our flow rate equation. From that we can find the velocity. So our velocity comes out to be 10.2 feet per second, and now we can use this value. We can use this value after number rho v d over mu. We will use the same values at t is equal to 100 Fahrenheit for our density. As you can see, our density is 2.05 at this 100 Fahrenheit. So we'll put this value of density, velocity, and the diameter is given, and similarly the viscosity value. So our Reynolds number comes out to be 1380, which is less than 2100. So this is the laminar flow regime, and we can now safely say that our flow is laminar. And now let's move on and find our wall shear stresses. So hence the flow is laminar. So from equation 8.5, the wall shear stresses, this is the equation that we already derived for our laminar flow. This is the equation of wall shear stress. So the pressure drop into the diameter divided by 4 into the length of the pipe. So we have all the values of pressure drop, diameter, and the length of the pipe. So we can easily find the wall shear stress that came out to be 1.24 pound per square foot. So part C is finding the net pressure forces and the shear forces. So what we will do, we know that pressure is equal to force per unit area. So we will actually rearrange the formula and write it as force is equal to pressure into area. So we will just do that. We have all the values of pressure, delta P, and the value of diameter, and pi by 4. So this will be our pressure force, and similarly net viscous force will be equal to the shear stress into the area. So that is 2 pi r into tau w, 2 pi r l into tau w, and this is our shear stress. We know its value, and after solving this, all the values are given. After solving this, what we will have our viscous force value of 5.84 pounds. So this is an example from your book, and here we have used some of the equations that we derived in the laminar flow conditions to solve this example.